So that's the first analysis that we have to run. We have different options. We have created different PV arrays, at least 2, 3 options, and then we can make decisions. So the decision is about, first, as I told you, the total energy production. So we need to assess the total energy consumption. We can do that with Revit, Design Advisor. So we have talked about how to do this with different software. But now we have to match the energy production to the energy consumption. And we have to assess the effectiveness of the solution. So the effectiveness of the solution is the energy that we can produce per area. So here we have 73 square meter. We can have a square foot or whatever, but this is the unit of area. In this case, it's a square meter. So how can we assess which solution is more effective? Okay, so we have to go to the calculator, and we have to divide the energy production divided by the area. So if this one it's 11,569 divided by 52. So this is 222. So the first option is 222 kilowatt hour per square meter. So this is the unit of area per year. So now let's look at the second solution. The second solution is 14,620 divided by 73, and this is 200 kilowatt hour per square meter and year. So which solution is the most effective one? The first one. Okay, so the highest value in terms of kilowatt hour per square meter or square feet or per unit area is the most effective solution. So, but if we need 14,000, then we have to go for this, because with this solution, the maximum production is 11,000. Okay, so we need more area. So this solution, it's less effective, but we have more area, so we have more production. Okay, so we have to understand this, because it's there are many factors. It's not just the production, or it is the production, but probably this is the first factor that we have to look at. If we have the energy consumption, we need to produce as much energy as we consume, and then we have a zero energy building. But then we have to do this in the most efficient way. So the efficiency is measured by the kilowatt hours per unit area. It can be square meter or it can be square feet, but we have to keep that in mind. Okay. So first, zero energy building, that's the goal. We need to match energy consumption, energy production. Second, we have to look at the efficiency. The efficiency, the highest energy production per unit area, the better. It's more efficient. It's better in terms of economics, because we are saving money for our clients. And are there any other factors? Yes, aesthetics. Okay, so if we have something that is very effective, that meets the zero energy building goals, but it's very ugly, we might say, okay, this is not what we want. Okay, so there are different aspects, and it's your decision. Well, it's your decision. It's you and your client's decision. And that's it. So there is nothing we can do about it. We have that goal. This is a good goal, zero energy buildings. And then how we achieve this goal of the zero energy building, it's another story. So in this course, we are giving you some tools to assess whether you have a zero energy building or not. Then about the aesthetics, or about, well, you have other courses, you have design courses, and I think the challenge now will be to integrate renewable energies into projects that we consider beautiful. Okay, so that's a challenge that we haven't we have not, we don't have a clear solution for that. So there is no, we can say, okay, so there are objective parameters to assess whether a decision is good from the energy point of view or from the aesthetics point of view. But some decisions that are good for both, it's a challenge of modern architecture, of contemporary architecture, that we have not had before, because that concept of integrating renewable energies into projects, into architectural projects, it's not new, because that technology has been around for 50 years, but now it can be massively produced at a good price, and it's becoming mandatory. Okay, so it's not an option, it's something that it will be mandatory by 2050. So there's still a lot of well, we don't know how to do it. We can have different ideas, but we need examples, and so that's why we are asking you to integrate these kind of things on existing buildings, because we don't know how to do it well. Okay, so that's the first analysis, and we have the Revit analysis, and that's a great tool, and we can make a decision very quickly by analyzing a few options. Okay, so here Max has analyzed 2 options, but we can have more. We can tilt the roof, or we can create an array with only one angle to see. Okay, so there are different options, but at least you should be able to do that, to analyze the best option in terms of energy efficiency, in terms of energy production, and then the efficiency. Today, I'm going to show you how to analyze this option, or how to go even farther. And we have this PV Watts software. PV Watts, a wonderful tool. It's for free, and it's developed by the Department of Energy. So can we rely on the US government? Well, in terms of the PV Watts, I think we can, but and it's very easy. I think you're familiar with this tool. We only have to type the location, if it's in Concord, New Hampshire. So check that it's the right Concord, because there are different Concords in this country. Then here we have the system info, and we have limitations. I mean, in Revit, we can create any shape with different angles, and we can create complicated things like this one. Okay, so here we have 2 different areas with 2 different tilts, and we can do that with Revit easily. Can we do this with PV Watts? We can, but it will be much more difficult than, because we basically here we have 2 different arrays, and we have to check this array with that angle, and then the other array with the other angle. And can we take into account the shadows that one row of one array is casting on the other one in PV Watts? Not really. Okay, at least we can draw, and we can have that feeling. In Revit, we can create like a 1-year simulation, and we can see, you see that there's a different color here. So that means that that color, or we have part of the year, this array is casting shadow on the other ones. So that's why we have different color here. So every time we cast shadows on this, that panel stops producing energy. It's not that it would have half the panel in shape, it produces half the energy. No, it produces 0. And that's something very important. Okay, so if we have 30% of the panel in shape, the energy production of this panel is 0. It's not 70% out. If 30% of the panel is in shape, then the other 70% is producing some energy. Nope, 0 energy. So we have to be careful with that, because there will be moments in which our PV array is not producing anything. So can we have that in PV Watts? Well, we have this factor, the system losses. So why is that system losses? Then out of the energy that we produce, out of the energy that, or the sun that we receive, we have to convert the direct current into alternating current. So we need a current inverter. So every time we add a device, we lose some energy. If we have shades, we have another percentage of system losses. Then if we have batteries, we have to store that in the battery, and then we have to release that energy stored in the battery to the devices. And then we have some losses. So every time we add a device, we generate losses because we have to do something with the energy that we receive. We have to transform the energy. We have to store the energy. So every time we do something with that energy, we have losses. And so we can increase the percentage of losses, but it's not very accurate. I like this in Revit because in Revit, if we have this yearly analysis, it takes into account the shades and other things. Okay, but anyway, as I have told you many times, we don't have a tool, the perfect tool to do everything. So we have to rely on different tools, and that's what we are going to do today. We are going to compare the PV performance in Revit with the PV performance in PV watts. But that's the only parameter in which we can take into account shades and other aspects of the system. So I'm not going to touch this. By default, we have this 14% of losses, so that's fine. Here we have a loss calculator. What is it? Okay, so those how they have estimated the system losses. We have shading, 3% of shading. Okay, we can have more, but the goal would be to have 0% of shading. Okay, so it's not okay. So let's make it less efficient. 50% of shading. Don't do that. It doesn't make sense. Snow, percentage of snow. We are in Concord, New Hampshire. So snow, it's a deal. So how can we take that into account? Reduction in the system's annual output due to snow covering the array. The default value is 0, assuming either that there is never snow on the array, very unlikely, or that the array is kept clear of snow. I recommend you that. Okay, so when it's snowing and the snow stops, someone from maintenance should go and get rid of the snow. If it doesn't happen and the snow is there for 1 month, is it worth having a PV array? No, it's not. So can we have a system to melt the snow? We can have a system, but again, it will be more expensive. But they have considered that they have 0% of losses from snow, and it's this. The array is kept clear of snow. So we have to try to do this with maintenance. Mismatch, what the hell is that? Due to slight difference caused by manufacturing imperfections between modules in the array that cause, okay. So we can have imperfections or flaws in the manufacturing of the panel. Wiring, yeah, so we need wires. Okay, so every time we have a wire, every time we transport energy from one place to another, we have some losses. 2%, it's acceptable. Yeah. Connections, the same thing. Every time we connect something to something, we have some losses. Okay, so these are different parameters that can affect the system efficiency. So they have we have this 14% of losses by default. Okay. Then this is the PV array itself. This is the tilt, and this is the azimuth. If you can, you have to orient the PV array to the south. If you do that to the north, you can generate some energy, but it's not worth it. We saw when we analyzed the energy irradiance that we have in the southern facade or the northern facade, the southern facade has 10 times as much energy as the northern. Okay, so there is no point on, and the northern PV panel costs the same as the southern one. So there is no point on spending money on something that produces 10 times less energy than the other one. So south, it's the option. Then east and west, we can track, but if you can select, orient all the panels to the south. And then the tilt. Here you can't analyze two different tilts at the same time, as we can do in Revit, but we can analyze the tilt. The module type, we have standard, or we have a premium, or we have a thin film. Standard and premium, premium means that it has a very high energy efficiency. So we can read that on the specifications. And then we have the thin film, the difference between the crystalline and the thin film. Okay, so that's important. Crystalline versus thin film. So the difference between the crystalline and thin film solar panels. So we have here a lot of information on the okay, so monocrystalline and polycrystalline. So there are two crystalline technologies, mono and poly. Are there a difference between them? Yes, there are, but to us, the most important division is between the crystalline and the thin film technology. So the advantages, they are more durable, lasting 30 years, very optimistic, and have 20% efficiency compared to thin film, 10%. Again, the 20% efficiency, it's the highest efficiency that we can have under standard test conditions that happens 1 second per year or per decade. But what we have to keep in mind is that the efficiency of the crystalline technology, it's double than the thin film technology. So what's the point of using thin film technology if it's worse in terms of efficiency, in terms of durability, aesthetics? I always, the best company in terms of integration between architecture and architecture and PV panels, well, the best company. They are friends of mine. So I always recommend this company, Onyx Solar. So if you look at this company, so they are very good at integrating architecture, modern, contemporary architecture, and PV panels. So they have developed these hexagonal PV modules, and here they have products and services. We have the crystalline, or we have the amorphous. The amorphous and thin film, it's the same. So if we look at crystalline PV glass, this is the kind of this is what the crystalline module is. So we have these opaque cells. They are dark gray or black or dark blue grays. They are opaque. We can get some transparency by creating a gap between two PV cells. Okay, so here you can see the difference between the transparent glass and the opaque cell. So the more the larger that gap between cells, the more light we get in, but the less electricity we are producing. Okay. So this is you see this picture. So here we have a huge gap between the PV cell and the two rows of the PV cell. So that is almost transparent. Okay, so here you can see that we can use this gap to increase the transparency. Okay, that's fine. But again, we are losing energy. Okay, so don't be naive. Don't think that by doing this, we can produce as much energy as we can produce with an opaque panel. Doesn't happen. So this is the solar cell density. Is it efficient? It's not. So engineers don't like this solution because it's not efficient. But architects, we like this solution because it's beautiful. So there is always a clash between efficiency and beauty. Anyway, usually we have opaque technologies or opaque crystalline modules. That goes well, for example, for covering parking lots. We need something that it's not transparent. We need something that it's opaque. So that will be a great option. Okay. So this is the crystalline silicone. The amorphous silicone or the amorphous PV panel, it's something that can be completely transparent. So that's why this thin film or amorphous, it's in the market, it's available in the market, because in terms of aesthetics, it's great because you can tell that this is a PV array. Okay, so you can have a skylight or you can have a curtain wall that it's completely transparent and it is producing electricity, half the electricity that a crystalline panel would produce. But and you can use colors. Okay, so with the thin film, you have a lot of options in terms of aesthetics. But in terms of energy production, it's worse than the other one. But we like it. I mean, architects, we like this because we want to believe that a good technology, beautiful, transparent, energy efficient exists. It doesn't happen. Okay, so if it's beautiful and transparent, it's not energy efficient. And if it's energy efficient, it's not transparent and beautiful. Oh, that's something that we can debate. So that's the difference between the crystalline technology and the thin film technology. Is it worth placing thin film technology if the price is the same and the energy efficiency is half? Well, this is something that you have to ask yourself, okay? But here you can see different projects, and I think they are very good at integrating curtain walls, skylights into a good contemporary architecture. Okay, so they are based in, this is a Spanish company, but they are worldwide creating this kind of integrated PV arrays in different buildings everywhere. Okay. So if you want to, not only in commercial buildings, but also in single family houses or small projects, so they are very good at this. Okay, so there are companies that are interested in that, combining PV or integrating PV panels into contemporary architecture. But we are not going to use a thin film. We're not going to use it. And then between standard and premium, what does it mean? We can always go to this information. So that's the efficiency. Okay, so the standard crystalline technology, we have an efficiency of 19. This is 21, and this is 18. Again, very too optimistic. Okay. Especially the thin film, we can have 18% of efficiency with thin film technology. So let's stick to the standard technology. The array type, we have the open rack or roof mount or axis tracking. Well, the tracking, it's something very expensive that usually we don't have in buildings. Okay, a tracking PV array. We need a device like this, something like that, that moves as the sun moves. Okay, so that the PV array is always perpendicular to the sun. So if the sun rises in the east, and then it goes to the south, sets in the west. So they adapt the azimuth angle and they adapt the tilt. When you have a solar farm, when you have PV arrays in the middle of nowhere, in the middle of the field, this is very efficient. Yeah, because the more perpendicular the sun rays to the PV array, the more the production. Having this integrated in buildings, well, I don't mean that you can't do it, but I haven't seen this technology in buildings yet. Okay. But anyway, that will be this option of the tracking, and we can track one axis. So that means that the tilt is fixed, and then we adapt the azimuth, or we can track two axes. So that means that we can change the azimuth angle and the tilt, both. But if we are talking about buildings, we have to decide between open rack and roof mount. If we go to these samples for, so that will be an example of the roof mount. So we don't have a structure, a different structure. We make the most of the tilt of the roof, and then we place the PV panels on the roof. The open rack is what we have here in this building. We have an open rack, we have another structure, and we have air going underneath the panels. What is the best in terms of energy efficiency? Probably the open rack, it's more efficient. Okay, so we always need a structure, and then on that structure, we can place the PV panels. So that will be the open rack. Okay, so we create the angle that we want, and we need that structure. It's more expensive. It's more efficient because one of the problems of the PV panel is the efficiency itself. It's overheating. When the PV panel reaches a temperature, that is very likely that it happens in summer, then the efficiency goes down and it can produce zero energy if the panel is overheating. So having air going through that structure can help refrigerate or reduce the temperature of the panel. So that's why they say that this is slightly more efficient, but it's more expensive, because when we have the roof, we only have to place the panel on the roof. Here we have to create another structure. If we have a flat roof, we have to create that structure, and it's more expensive. So again, we have efficiency, we have aesthetics, and we have money. But that will be an example of an open rack technology. So fixed open rack, or in this case, this is the open rack because it's a flat roof with this tilt. So in this case, it will be an open rack. Where are we? Yeah, so in this case that we are working with, we will have the open rack. Okay, so we have analyzed this module type standard. If you are optimistic, you can say that it's a premium one. Array type fixed open rack. System losses we can keep with this one. Tilt, we need the tilt, we need the angle. We can change this to, let's say, 30. The azimuth, that's the orientation. If we can keep 180, this is south. Okay, so try to keep this south orientation with 180. If it's facing east, it's 90. If it's facing west, it's 270. And don't place PV panels facing north. Please don't do that. And now that's the key of this, the DC system size in kilowatts. Okay, so what's that? That's the number, that's the direct current production of the PV array in kilowatts. So that depends on two things. It depends on the production of each panel and the number of panels. So where can we get this information? We can get this information from catalogs. And what catalogs? You have this PV solar brochure on Canvas, so I'm going to download it. And if you open it, this is WHI. It looks like a Chinese brand, but here we have information about the modules, and not only about the modules, we have everything that makes up a solar. It's the inverter. Inverter is the device that turns direct current into alternating current. We have charge controllers. This is important because if we have an overproduction and the electricity system can cope with such a high energy production, we need to control this charge. So we need to divide this charge so that the system is not damaged. And then we have the mounting systems. That would be the rack, this open rack or whatever. And we have electrical components, storage systems, batteries. Okay, so here in this, you can find information about everything that makes up a PV system. It's not just the panel, it's about everything. But that's the information that we want so far. Okay, so here we have the area of the panels, the size. Usually those panels are around, so the size of a panel in this case is 1.6 meters by 1 meter. And how much is this? This is 3 feet by 5. Okay, so one panel, it's around 15 square feet. Kind of. Okay, so that there is a standard dimension of panels. You can customize your panel. It will be much more expensive if you, I want hexagonal. We have seen hexagonal panels. You can do that, but it will be much more expensive than the standard panel. Okay, so let's stick to this dimension. So let's stick to this area of 15 square feet per panel. And now we need the production. We talked about the STC, the standard test conditions, but here we have another thing. So when we have these two electrical characteristics, or these two power, this is the maximum power, 185 watts, and this is the maximum power, 250 watts. The standard test conditions, I told you, that are conditions that happen once every year, every decade, or whatever. It's a perfect solar irradiance without any clouds, without any pollution, with the right temperature for the cell. And okay, so basically we have these two things, the solar irradiance and the cell temperature. So this is the maximum production that we can have under the best circumstances, these standard test conditions. But in other manufacturers, they give us the NOCT. So what the hell is that? NOCT. NOCT stands for normal operating cell temperature. Okay, so it's the normal operating cell temperature. We assume that the temperature of the cell can change, especially if it's exposed to the sun, it can heat up. They reduce the irradiance. It's not 1,000 watts per square meter as the standard test conditions. It's around 800. And then they change the temperature, the wind speed, and the tilt angle. Okay, So those conditions are more realistic than the standard test conditions. 800 watt per square meter. It can be the solar irradiance that we have on a day like today. No clouds, but it's not a perfect day. We can have some pollution, or we can have some water vapor in the atmosphere. Okay, so 800 watts per square meter, it's something that we have on the Earth's surface. 1,000 watts per square meter is something that we hardly ever have. Okay, so the NOCT are more realistic conditions. So in this case, we have the maximum power, it's 185 watts, or 2,050 watts for the standard test conditions. If we are comparing the performance of two different panels, we have to compare the same condition, either the STC or the NOCT. Okay, so if we only have information about the STC, we have to compare this performance to the other performance. And if we have information about both, I would be less optimistic and I would use this element. Okay, so what are the factors here? We have this panel. This panel is 1.6 meters, around 3 feet, by 1 meter, around, no, 5 feet, sorry. And 1 meter is around 3 feet. So we have 1.15 square feet of area, and the PV production under these NOTC or NOCT conditions, it's 185 watts. Okay. So now we need to know the number of panels or the total power that we have in this PV array. How can we do that? We have to analyze again this. So let's check this solution. We have 73 square meters. So it has 73 square meters in this PV array. What is the area of this panel? It's 1.6 square meter. It's 1.6 meters times 1. So the area in international units, it's 1.6 square meters. So how many panels do we have? If we go to the calculator, there are 73 square meters divided by 1.6. So we have 45.6 panels. Let's say 45. We don't have 0.6 panels. So we have to round down, not to round up. Okay, so we have to round down. So we have 45 panels. If we have 45 panels and the production of one panel is 185 under the NOCT conditions, now the total production of this PV array is 8,325 watts. What do we have to introduce in the PV watts? This is the DC system size in kilowatts. So if it's 8,300, this is 8.3 kilowatts. Okay, so it's very important that we understand this. We can control the tilt. This is up to us, is the project itself. If we can control the azimuth, the module type, the array type, and the system losses. Basically, we are not doing a lot of things with that. We just select, if we are very optimistic, we can select the premium. If we are less optimistic, we can select the standard. We can select if it's an open rack or a roof mounted array. That's easy. And the system losses, we can leave this default percentage of system losses. That's fine. But the DC system size, it's something that we have to understand. So we can address this in different ways. So we can select the total area, then we can select the panel, and then we can find out how many panels we need, and then we multiply the number of panels times the percentage, the PV production of each panel. This is what we have done so far. Okay, but that's it. We need this information. We need this catalog. Okay, so for the next assignment, you can use this one, or if you don't like this, you can download another different catalog. But we need this information. We need the area, we need dimensions of the PV panel, and we need the maximum power, either in NOCT or in STC conditions. I don't mind, but you have to state what kind of conditions they are using. Here in this brochure, we have other panels, and you see we have different sizes of panels here. So this is the maximum power at STC, and these are different. So that produces 15, 30, or 55. Does it mean that the 55 it's better than the 15? No, it's just bigger. Okay, so you see that we have different sizes here, and probably the other one it's even bigger. Yeah, so this is 450 millimeters. So this is 0.4 meters times by 0.3 meters. So this is much smaller than the other one. Okay, so that's why the production is lower. But we need to know the dimensions and the PV production at different conditions, either the STC or the NOCT. But we need a catalog. We can't do that without a catalog. So here you have different options with different measurements and different productions. Okay. So I have selected the first one, but you can scroll down. But in your report, we need this information. You have to copy and paste that screenshot on your report, because I need to know what kind of panel you have selected to find out if it's right or wrong. Okay, so we have selected this DC system size in kilowatts. In this case, we have the total area, we have the number of panels, we have the production of each panel, and then we can figure out this number. We have all this information, and then we go to PV watts results. So in this case, our production it's 10,700 and 10,700 kilowatt hours per year. Can we compare this to the Revit? Well, do we have any information about the PV production in Revit? We do. I will open Revit, but we do have some information about the PV panels in Revit. Okay, so you remember that there were some settings here, and here we can check the PV production of that. We have the same area, so I have used the same area, this 73 square meters. So with this software, the production is 14,000. In PV watts, the production is 10,000. It's a huge difference, but again, what do? Do I rely on Revit? Revit is more optimistic than PV watts. Do I rely on PV watts? Well, here we have different, the angle is not different, so I know the angles here, so I should check the same angle in PV watts and the same angle in Revit to compare things. Probably this production is higher because those two angles work better than just the 30 angle, the 30-degree angle that I have used in PV watts. But anyway, this is what we get from PV watts. And this is better, well, it's better. Here we have information about the solar radiation. Okay, so that's the solar radiation that we get outside the panel. Okay, so that that number that we have there is the solar radiation that strikes on the panel. And this is the total AC energy that we produce, alternating current energy that we produce. Okay, so that's it. If we multiply the monthly, the daily performance in 1 month times 31 days times the area, then we have this total number. So in January, if we multiply 3 times 37, let's do it again, 3.37 times 31 days times 73 square meters, we have 7,626. So that's the total energy that the sun gives us for free. But now we have a device, and that device turns that energy, that solar energy, into electricity. And then we have wires, and then we have inverters and charge controllers and all that stuff. So at the end, we end up producing 700 out of 7,000. So this is about 10%. So that's the actual efficiency of the PV panel, around 10%. Okay, so this is how it works. Okay, it's better than nothing, but usually engineers don't like this technology because of the efficiency. If we compare the efficiency of a PV panel to the efficiency of a boiler, a gas boiler can have an efficiency of 90%. So that means that out of 100% of potential energy from the fuel, we can turn this into a 90% useful energy for us. A PV panel can do that only with the 10% of the available energy. Of course, the energy that the PV panel is using is the energy that comes from the sun. It's for free, it's renewable, and it's going to be there, not forever, but for millions of years. Fuel is not renewable, it's not clean, it produces other kind of greenhouse gases, but the efficiency is very low. Okay, so we don't have to be naive. Oh, what a wonderful source of energy. It is a wonderful source of energy, the sun, but the technology that we have on Earth to make the most of that sun it's inefficient. It's not great. Okay, so there are better alternatives in terms of efficiency. And the efficiency is turning potential energy that this source of energy has into useful energy for us. So that's it. Is it everything that we know? In PV watts, we have great information here. We can download monthly or hourly analysis. If we download this monthly, so we get this Excel file. So we can open that Excel file and see what happens. This happens. Okay, so here we have these numbers as the Excel file. Is it better? Well, I think so, because here we have the all that information. We have the daily average irradiance. If we open all these, I'm going to wrap text. Okay, so that will be better to understand what we are doing. So here we have the month, January, February, up to December. Here we have the daily average irradiance. Here we have the DC array output. What is the DC? So we have more information here than in that interface. In that interface, we have just the solar radiation and the AC energy. The DC, it's the direct current. So as you can see, there's the direct current, it's always higher than the alternating current because here we have the inverter. Okay, so we need a device to transform direct current into alternating. And why do we have this? Because 90% of the devices that we have in buildings run on alternating current. If we had devices running on direct current, we will increase the efficiency of the system. But if we have alternating current devices, then we need to lose some of the efficiency because we need that inverter. So if we want a visual analysis of this, we can always select that. We can insert a chart, recommended charts, and I think that will be good. Okay, so let's do something better. Let's try to analyze this data because we need more. So here we have a number of days. Okay, so what are the number of days in January? 31, in February, 28, March, 31, 30, 31, 30. September, it's 30, October, 31. Okay, so these are number of days of the month. And here we have the roof area or the PV array area. So the PV array area, well, we have the same area every single month. It was units are important. Okay, so if these are square meters, we need square meters here. So that area was 73 square meters. So we can drag it down and we have 73 square meters. So what is the total? Solar radiation? So it's the same thing that we have done before. We can type here equals, and we can multiply this times the number of days times the area. Okay, so that's the number that we had there, 7,626. Well, here is 21, but doesn't matter. So that's the total solar radiation. And if we drag this down, here we have the total solar radiation every single month. And what I want to do now, I want to copy this here. No, not the DC output, sorry. I want the AC output. There you go. Okay. So now here I have the total solar radiation and the AC system output. Now I want to select these two columns. I want to go to this chart. And here we can see visually the difference between the solar radiation that we have available and the actual electricity that we can produce. Okay, so this is a little discouraging because, okay, yeah, looking at numbers, 70,700, but visually we see, okay, we have, I mean, as human beings, we have a lot of room for improvement because out of this solar radiation, we can turn into useful electricity only this part, the orange part. Okay, so here we have the total solar radiation, and here we have the AC output, the system. Okay, so well, but I like it. I mean, it's a useful visual chart looking at this, we can realize that the system has a lot of limitations. Okay, but that's fine. At least we are aware of that now. Now, it would be great, to compare well, here we are comparing the solar radiation that we have outside, the energy that we get from the sun, and the actual energy that we can turn into electricity. Okay, but now I would like to compare the electricity that I can generate over the year with the energy consumption. Okay, because well, looking at this, I don't know if I'm designing a zero energy building or not. What I do know is that I can use only 10% of the energy that we receive from the sun, which is fine. But now, what is the percentage of energy that I can cover with this PV array? How can we do that? I'm going to insert here different columns. Okay, and now I need here a different, let's say, energy consumption. So let's try lighting. Heating and cooling. Okay. So here we have the lighting, the heating, the cooling, and I can insert another one. So this is the total electricity consumption. So where can I get this information? I can get this information from a simulation tool. For example, Design Advisor. So let's see if I can find that information from somewhere. I'm going to insert a new, and this is the area, the floor area. Okay, be careful because here we have different areas. That's the PV array area, it was 73, but the floor area of the building, it was, let's say, 80 square meters. Okay, so let's say that this is 80 square meters. And it's 80 for all months. But now we have lighting, heating, and cooling. Okay, so if we go to the Design Advisor, this is what we have. We have the heating energy, we have the cooling energy, and then we have the lighting. So I'm going to do this. Okay. And I'm going to copy all these values here. So this is the heating energy. In January, we have 49. In February, we have 41. In March, we have 30. In April, 15. In May, 5. In June, July, it's 0. In August is 0.3. In September, it's 0.6. And then we have 12, 22, and 42. Okay, so that's the heating in kilowatt hours per square meter. Units are important here. So I'm going to type kilowatt hour per square meter. The same for cooling. In cooling, the units are kilowatt hour per square meter, and in lighting, here we have a kilowatt hour per square meter. Okay, so that's the heating, and now we have the cooling. Cooling energy is 0, 2, 3, 4. Now we have 1.4, then 7.9, let's say 8, 25, 24, 5, 4.2, and 0. Okay, so that's the cooling energy. We have heating especially in winter. We have cooling in summer. That makes sense. Lighting, it's going to be steady throughout the year. Okay, so in lighting, we have 5.5, 4.7, 5, 4.6, 5, 5.2, 5.7, 5.7, 5.3, 5.4, 5.3, and 5.6. Okay, so those numbers seem correct because I have heating in winter, cooling in summer, lighting throughout the year. Those numbers are kilowatt hours per square meter. And here we have the area. So what's the total energy consumption? I have to create a formula here. So that equals parentheses. So I have to add everything up. Okay, so here I'm adding up the lighting, the heating, and cooling because everything is electricity. So we have kilowatt hours. So I have this plus this plus this times 80 because we have 80 square meters. So let's say that this is lighting plus heating plus cooling, parentheses, times area. There you go. And now we scroll down and we have these nice numbers. Okay. So looking at this, look at this total energy consumption. We can look at this. We will create a graphic, but I think this will be, well, that's clear. In January, we need 4,300 and we produce 700. In winter, we are closer. Well, there are months in which we get a zero energy building. So in May and June, we are close. Well, in May, we have a zero energy building. And in June, we are very close to a zero energy building. In October or September and October, we are close to a zero energy building. So that's it. But if I want to see that clearly, I have to do this. I can select data. I can add one more thing, the total. I will select this total energy consumption. And then here, I'm going to select all these values. And I click OK. And that gives me a good understanding of what I'm doing here. Okay, look at this. This is the energy that we consume. The sun is giving away much more energy than the energy that we consume in buildings. What's the problem? We can't use these energies. Yeah, we have a lot of energy from sun, but can this energy from the sun turn on these lights? We need a device that turns the solar energy into electricity. So that device is very inefficient. So there are months in which we are there, we have a zero energy building. but in winter, especially in winter, we are far from the zero energy building. In summer, we are close. So that's the outcome of this analysis. The outcome is, if we could make the most of all the energy that we receive from the sun, we wouldn't have energy issues on Earth. The problem is that we haven't figured out yet how to do it. But if we could, look at this. So the energy that we are consuming, it's nothing compared to the energy that we receive from the sun. Now, what is the technology that we have available? We have this orange technology. So this orange technology in May, June, or in April, May, June, September, October, we're almost there. When we really need heating and when we really need cooling, we're still far from the zero energy building. So what do we have to do? Can we reduce more the energy consumption? That's one option. But we have designed a very good building. We have designed a building that meets the passive house standards. We have created shading devices. We have done a lot of things. It's not enough. Okay, so we have to increase the energy production. So if we try to use all the area that we have available so with this roof area, this is what we have analyzed, 73 square meters. So looking at this, we have 73 square meters of PV array on a building that has 80 square meters of floor area. So this is the result. Are we far from the zero energy building? We are far from the zero energy building, but believe me, if it weren't for all the measurements that we have taken, the high R value, solving thermal breaches, using triple glazing, providing the building with shading devices, we would be even farther. Okay, so at least there are some months in which we can get the zero energy building. Probably the problem in this building, that specific building, is the heating. So we need more heating here. Probably we can solve this with something that it's not electric, okay? Because we are assuming that all our systems are electric, heating, cooling. It would be a great solution if we could use solar collectors, because with solar collectors, we can produce hot water for free. If we produce hot water, we can use a hydronic system. So combining solar collectors and PV panels, it's a good solution. It's not mainstream in this area of the world because we have problems with the freezing, okay? But again, we have limitation in our technologies. Sometimes we think that, oh, we are human beings, we can fly to the moon, we are limited, small, illustrated creature in the middle of the universe. So we are on our way to do something decent, but we are far from controlling all the resources that we have available. But not here, because here with the temperatures that we have in winter, using solar collectors, it's something that nobody recommends here because of the freezing and the pipes bursting and all that stuff. In other latitudes, it's easier. In other latitudes with warmer weather, it's easier to get to the zero energy building in winter. Then we have other issues in summer. Okay. So here, summer, I think it's we are quite close to become a zero energy building. In winter, we are not. I remember that when we were analyzing the peak energy consumption, summer or cooling was more difficult to get the peak energy consumption for cooling. But the peak means that at one moment, 1 second, we have this peak consumption. But then we have to multiply times the hours in which we need the cooling system. So that's the difference between the energy, kilowatt hours, and watts or kilowatts. So probably if we want to meet the requirements, the passive house requirements in terms of peak consumption, cooling, it's more demanding than heating. But then we have to multiply the hours that we need the cooling system. So we need more hours of heating system than the cooling system. And that's why we have this two different demands or two different requirements, the peak consumption and then the energy consumption. So in terms of peak consumption, we're talking about power. So probably the power that we consume at one moment for the cooling system, we are far from the passive house requirements. But when we analyze this, so that's why I like this better than the passive house requirements. The passive house requirements are very demanding. And basically they are telling you not to create any crazy things with curtain walls or openings, so small openings, very tight building, very high thermal insulation. But if we analyze this performance over the year, there are more things to a good design than just reducing the number of windows or whatever. So there are more things that we can do. So the goal is that the gray bars and the orange bars are similar throughout the year. Okay, so this is a very good outcome from PV watts. And by combining PV watts and Excel, we can have this. And visually, we can see if we are far or we are close to achieving this goal. But there is more that we can get from PV watts. So I have downloaded these monthly results, but now I want to download the hourly results. So by downloading the hourly results, I can open another Excel file. And here I have the same information. Well, I have the same. I have much more information. I'm going to wrap text and here. Okay, so here we have a lot of things. We have the beam irradiance. So this is the direct solar irradiance. For example, in a southern facade, this is the diffuse. So that would be the diffuse irradiance. That's the northern facade's irradiance that we can have. The ambient temperature, that's important because it affects the performance of the cell. We have the wind speed, that's important because it affects the performance of the cell. We have this albedo, which is the reflected solar radiation. This is the irradiance of on that plane of the array. This is the cell temperature. The cell temperature is affected by the solar radiation. It's affected by the ambient temperature and the wind speed. And that's the DC and the AC system output. Okay. Well, here it's incredible the kind of information that we can get because if this is month 1 and I want to create a graphic of January, so I have to select all these cells from January the 1st until January the 31st. You see that January the 31st is here. So I have selected all these values, and then I can insert a chart with bars. So this is it. I want to change because I want columns. Okay, so when we are analyzing a lot of data, we have to make it wider and bigger to understand what we are doing. Okay, so this is the AC. I can change the chart title because this is the AC system output. So those are the hours. Okay, so we have hour number 1, so hour number 25. So this is 1 day. From 1 to 24 is 1 day. From 24 to 48 is another day. Up to 72 is another day. Okay, so we can see different days here. So there are days in January in which we have a high system output, and other days in which we have 0 or almost nothing. Why? This is a cloudy day. If it's snowing outside, we don't have any energy production. If we have sunny days, we have a very high energy production. Okay, so we can have this information throughout the year, monthly and daily. Okay, so with this Excel file, we have the monthly information in terms of energy production. With this one, we have daily information, which is much more powerful. There are a lot of more things that we can understand by doing this. So can we compare the daily production to the daily consumption? Yes, we can. How can we do that? If we go to this in Design Advisor, for example, in January, we have the heating, we don't have lighting. No, we don't have the lighting here. Let me see if we can get something. I want to use this graphic again. And here I want to add the lighting. In kilowatt hours, right? And heating or HVAC, let's say HVAC in kilowatt hours. Okay. So what's the lighting? It's 7 kilowatt hours per square feet. Your building was 800 square feet. Okay, so we are talking about Now, this is not. That's not the statistics. We need the hourly consumption. Anyway, I'm going to make up this number. Imagine that we have around, let's say 20 kilowatt hours. And we have this from 7 a.m. The building starts at 7 a.m. and the building ends at, let's say, 6 p.m. or 7 p.m. Okay, so we have 12 hours. So if this system is on for 12 hours from 7 a.m. until 7 p.m., that's the consumption of lighting that we have every single moment here. The HVAC, let's say that it's 200, and I'm making it up, okay? And I consume 200 again from 7 a.m. to 7 p.m. So if I'm doing this on January the 1st, if I select data and I add one more series, no. So now I need the total consumption. So for the total consumption, I have to add this up. I have this plus that. And then I move it down. And now I can add this select data. I can add one. I can add this total consumption. Then I can add 1 day. So this gives me a better analysis of what I did. Okay, so if I do this over 31 days, here I can have the energy demand compared to the energy production. Okay, so you can see how on this January the 1st, there are moments in which I need this demand and I don't have any energy production because at 6 p.m. I'm not producing any energy from the sun, it's dark outside, but there are moments in here in which I have more production than energy consumption. Okay, so that will be the next step. We're not doing that today because we don't have enough data, but somehow we need to get the lighting and the HVAC consumption, not just monthly as we have here, but we need this hourly. So we will figure out how to do that with good numbers, but that will be the second part of the analysis of that building. You can do the monthly analysis, this monthly analysis with the PV array that you have designed, and you have to compare this to the numbers that you have from the lighting, heating, and cooling that you get from Design Advisor. I have to go over all your assignments and I will give you feedback so that we can rely on those numbers, but I think we can rely on your numbers here. Okay. And then we have to do that daily. So the daily analysis, yeah, we have to get that data. We need a schedule. So the schedule is from 7 a.m. to 7 p.m. But then we can compare the energy production and the energy consumption on a daily basis.